Thank you. So, I would like to go a little bit back to the climatological part again. Presenting this work on aerial rainfall from radar in the context of urban drainage analysis and design. Some reflections about that. The background for this is that we previously didn't have a practice in Denmark to include aerial rainfall or spatial variability of rainfall in design of urban drainage systems. But due to the fact that we have larger catchments, we have centralization of wastewater treatment plants, we need to consider the spatial component of the rainfall also in design. And that might aid that we can at some point do some more reliable urban drainage design and prevent oversizing, for example. So from this approach, we can ask the question whether we can use weather radar to investigate the spatial variability of rainfall related to the impacts of urban drainage design and analysis. And I will look at that from three approaches, focusing most on the first one, which is a statistical approach, where we use, let's say, rainfall statistics from IDF curves and multiply them with an areal reduction factor that we derive from radar data. And then a deterministic approach where we use radar data as input to models, and finally a stochastic approach where we also use radar data into a model, but I'll get back to that. The data set that we're using is 15 years of radar observations from Denmark, from the Danish Meteorological Institute C-band 1 radar in this case. We have a 500 by 500 meter rainfall product in 10-minute values for these 15 years, but not a continuous data set. We have a lot of data that we filter out due to noise and due to poor bias adjustment and so on. So it's a data set consisting of some 500 single days of rainfall during these 15 years. And then we do an adjustment with some rain gauges here in the Copenhagen area or Zealand in Denmark. And then we do what we call an advection interpolation. So we take the 10-minute snapshots from the radar and interpolate using basically our nowcaster to interpolate to 1-minute values. So we get a much more smooth, let's say, track of the radar images. And that helps our mean field bias adjustments also. So we do a daily mean field bias with rain gauges, and then, as you can see on the plots here, we improve both accumulations and peak estimations during this interpolation, so that we don't, let's say, skip any rainfall. Yes. So, to the statistical approach. Well, in Denmark we have a tradition to use IDF curves for design of systems, but now we'll look at estimating an areal reduction factor. And that areal reduction factor is defined as the ratio between the mean areal rainfall and the point rainfall for a specific duration. And then we use a storm-centered approach to derive these RIF curves from radar data. You could also use aerial fixed or a fixed geography, but in this case we use a storm-centered approach. So we base this on approximately 500 days and for some 12 different durations, and then derive these RAF relationships for a number of storms, large number of storms. So the procedure is that we average radar data in space and time, And then we do empirical RAF curves. You should have seen some gray lines behind the ones here. They're not really visible. But basically we fit an average of RAF curves for different durations and then fit that to this exponential function over here. So basically the RAF is the intensity average over an area and a duration divided by the point rainfall times a bias here. And that bias is taking care of that we don't actually, when we look at radar data, we don't actually have the true point rainfall. We have an average over 500 by 500 meter. So we do some bias where we look at the correlation between the gauge and the radar for different durations. And the smaller the duration, the larger the bias. So when you do daily adjustment, then we have a bias of 1. So this is to take care of this, let's say, subpixel variability. Then further on, we derive this correlation length as a function of the duration, and then we can do a fit of that in this power function here, and then derive, I'll not go into the details with the math, but derive a general function of the RAF curve as function of area and duration. And then this is the results. So we have areal reduction factors for different rainfall durations. So for the 1 minute values, we have a fairly low value, fairly low curve. And for 24 hours, we have a higher curve. And then we can, doing some math, we can use this 3-parameter equation to estimate this. Obviously, we have some large variability from storm to storm, but this is presenting the mean of these areal reduction factors. So how can we implement this? We could do it directly into design. So multiplying the areal reduction factor to the IDF curves, and then get different curves for different areas. And correspondingly for a type of design storm that's very popular in Denmark, the CDS storm, we can calculate them for different areas. An example of application, this is the catchment to a treatment plant in Denmark. We have a catchment area of 1,100 hectares, a concentration time of 60 minutes. So we can see what is the areal reduction factor, and that's 0.76. So that means a 25% approximately reduction of the rainfall, the design rainfall in that point. Yes. The second approach, where the other one was rather statistical, this is a more deterministic approach where we use radar data as input to an urban drainage model. And basically we would use this for design of an existing drainage system. So we have a catchment here. This is a large catchment in Copenhagen, 82,000 hectares, or 8,000 hectares, sorry. And we use radar data from this 15-year data set to the model of this area. And you can see this is showing the pixels over the catchment. So in this case, we're simulating 250 events approximately with events with more than 5 millimeters of rainfall over this 15-year period. And some results here, we compare input to the model from a single rain gauge to the distributed input from a radar. And this is looking at the part of surcharging manholes in the events. And this is looking at simulated combined sewer overflow. But what we see is that we get an overestimation when we use the single gauge input. So basically these biases here correspond somewhat to what we derived before as the areal reduction factor over the whole catchment area. It's very difficult to assess return periods because we have this data set of single days and it's not continuous because we sort out some different data. So we don't do that in this case. And still, if we want to do extreme event statistics, we have rather few data, 15 years of data compared to the rain gauge series where we have now 40 years. And we would like to, let's say, design drainage systems for maybe 10-year return periods. So, in order to solve this problem, we are looking into what we call stochastic transposition. And this is a method developed by Dan Wright in the US, where he, let's say, moves stochastically storms around. So not looking at a fixed area as we did before, but saying, okay, this storm we observed elsewhere could have as well have been observed over this catchment that we're looking upon. So we're randomly moving storms around from let's say a catalog of observed storms to a specific catchment, and then we can do either statistics on the rainfall only on this catchment or this area, or statistics of the simulated response of the catchment. Well, basically, it involves a lot of simulations, some random resampling of the rainfall events. We're assuming that we have homogeneous climatology. And then it assumes something about using annual maximum series as a statistic foundation, let's say. And then it makes it possible to derive return periods longer than the length of the observed series, because you're moving the events around. So this is just an example where we sample from our data sets 60-minute rainfall and move them over a catchment. So we have quite a variability here of sampled statistics compared in this case to the Danish gauge statistics. The areal statistics is still work in progress, and also the catchment response statistics. So, to conclude, can we use radar data for these analyses? Yes, we could derive the areal reduction factors from radar data. I think better than we could if we had only gauge data. We can use the radar data as direct input to urban drainage models, but benefit is limited due to the length of the time series. So we're looking more into these stochastic approaches where we're trying to move the rain around randomly, both to as an input to drainage models, but also for, let's say, rainfall statistics. But as I concluded here, more work is needed, and that gives me a reason to come back here in 3 years, I think, to present some more. Thank you.
Okay, thank you very much, Soeren.
Thank you.
And also thank you for telling us your travel plan. We have time for one question or maybe two short questions. Yeah.
Just one peculiarity, there was a slide just before your example slide. Did you find it?
I have a few example slides. That one?
That one?
Yes.
So, can you explain the behavior we observed on the lower curve to the left?
That one?
Goes down?
Yeah. I should maybe have made a cutoff. This is aerial rainfall for 100 square kilometers. And you're looking at durations from 1 to 10 minutes. So that's not really realistic that you have, let's say, a response time of your system or a duration that's short on this area. What? This is the IDF curves, yes.
Yes, I agree, but over here,
For a specific return period.
it's okay. But the lower here, you have a convex concave shape,
Mm.
which means that if you go to 1 hour duration, the rainfall intensity will be smaller than the average rainfall
Yeah.
intensity.
But that's due to the fact that we have for the short durations this very low aerial reduction factor. So we should probably have made a cutoff and not showing for the very large areas let's say the very short durations.
Related to extrapolation beyond the validity of the analysis.
It could be, yeah.
And curves like that can be taken by somebody and used for.
Yeah. But you're right. It doesn't look good. Yeah.
Okay. Have you compared with NET area reduction factors?
Yes, I have. We have that in a paper just submitted. I chose not to present it here due to time limits, but I can show you.
Okay, I think we have to move on, and I propose to continue the discussion with concentration. We are now coming to August GS.